So this is the basis how we detect radiation. So it is based on interaction between the radiation and the medium. In essence, the detector material. And once more, radiation produces a signal in the detector material. This could be the detector material here. And the data processing system changes, or signal processing system changes the signal into a form that can be calculated, collected, or sorted according to the type of information we want to have. And usually what we want to have is a spectrum. So charged particles ionize medium and interact strongly. Particles like these, neutral particles, gammas, neutrons, they interact less and penetrates farther. So there are a lot of charged particles, of course, electrons, positrons, alphas, muons, protons, heavy nuclei, etc., etc. So they have different interactions, inelastic interactions with electrons. This is very vital to understand. It's an interaction with electrons of the medium material. So there is ionization process and excitation process. Of course, elastic scattering from the nuclei of the medium can happen. And then there are some other phenomena like Bremsstrahlung, Cherenkov radiation, annihilation radiation, these kind of things. And these are the main interactions for uncharged particles. I mean, in this case, photons. Photoelectric phenomenon, Compton scattering, and pair production. In case of neutrons, elastic or inelastic interactions are very important. All right. So you have to understand that especially environmental samples often contain beta-emitting radionuclides, which means that these betas may cause signals to gamma spectrum and also to alpha spectrum. You have to understand that too. In this case, Bremsstrahlung is happened, and the electron loses a little bit energy. Interactions, I mean ionization mainly, between alphas and electrons of the material are the main energy loss mechanisms. So it's alpha and electrons. Sometimes interactions happen with the nuclide, but not very often. So, as you know this, perhaps I can see easily if I am here. But the letters are so small, I have to go back, sorry. Yeah. But you can perhaps sit there if you like, so that you can see. Please sit there. So these are the examples of Compton scattering that I will consider in the next slides. Pair production and subsequent annihilation, which happens here, and photoelectric phenomenon. I know that you all know these things, but it's good to review these. All right. Here you can see photon attenuation in terms of square centimeters per gram in the vertical axis, and here is the energy of photons. So as you can see here in the low energies, less than 100 kilo electron volts or so, I guess this material is from lead. I forgot to put it in here. Main area in terms of energy is between around 1 MeV down to 0.1 MeV. Then pair production rises. So, do you have any idea what's this phenomenon? Yeah. Yeah. All right. So, interaction probability depends strongly on the atomic number and, of course, the photon energy. And as I explained in the previous slide, photoelectric effect is dominant in this area, pair production this area, and Compton effect this area. In case of germanium, which is the material for gamma ray detectors, mainly high resolution gamma ray spectrometers. So the limits are here. Okay, 100 kilo electron volts, 2, 3, 4, 5. After 5 MeV, pair production is dominant. So since we are in the present course, we are dealing with alpha and gamma ray spectrometry. The medium materials in the following slides are considered only germanium and silicon, which are the most relevant detector materials in high resolution. Of course, I will later talk about scintillation material things. And as you've noticed in yesterday's lab session, alpha particle energy loss in air is relevant, and that's why alphas are measured, alpha spectra are measured usually in vacuum chambers. But as I mentioned, electrons and beta rays has also a role. Okay, let's look at the interactions between alphas and medium matter. Ionization and excitations, they are the primary mechanisms. For alphas, the energy loss per ion pair formed is on the average 35 electron volts. And for example, if we have a 5 MeV alpha particle, it means that 100,000 and around 100,000 ion pairs is produced. And I'm sure that you know that the range of alpha particles is very short in air, around this size, some centimeters in air. So, and if you want to calculate alpha particle range in air as a function of energy, you can use, for example, this empirical relation. Now you have to understand also that interaction with nuclei, not only interactions with electrons, may happen. I will show it soon. Okay, these are ranges of alpha particles in this case for silicon, this case for air. This is the range. This is the original alpha energy in MeV. So there is a difference around 1000 between these two. So for example in silicon the range is 20-30 micrometers for 5 MeV alpha. So what is stopping power? It is the energy loss per unit path length. And in this case, it is expressed as units of megaelectron volts per meter. It can be calculated by using this equation. I will not go through these details. You can later check them. But the calculation is basically not very complicated. And this is so-called Bragg curve. So this is the path length, and this is the stopping power here. And at the very end of the path length, in this case, the original energy of alphas is 5.5 MeV, which is close to the americium 241 alphas. So at the end of the path, the ionization is emphasized. But alpha particles straggling, in essence, statistical fluctuations. It is the number of collisions between the alphas and the medium material, and this may vary the range a little bit, not very much, but a little bit. Okay, you can see here is a alpha source, very thin source. Alphas going this way to the material. And for example, this is a typical alpha particle track. It's a more or less straight line. And at the very end of the track, the ionization is very strong. These spots refer to the ionization. So alpha kicks out the electrons of the medium material. But for example, in this case, the interaction or here may happen between alphas and the nucleus itself. So the ionization is very sparse in the beginning of the path, but very dense at the end of the path. So this is totally different compared to the path of electrons. So this is alphas, very straight line, but electrons go like this. But in this course we are not dealing very much with electrons. We concentrate on photons and alphas. All right. How the detector properties and the material between the detector and the source influence the alpha peak shape. So in principle, the emission of for example, polonium-210, it emits only one alpha particle, and the peak should be very, very narrow. However, our detectors are not perfect. What we are seeing is like that. So there is a Gaussian part of this peak and some low energy daily. In this case, neptunium is a little more difficult to analyze because of several peaks. Some trans-uranium elements has only two main alpha emissions. All right, we discussed very shortly yesterday these things, but so what could be the thickness of a high-resolution alpha detector composed of silicon? So it is around 100 or 200 micrometers. And it should be not too thick, because it's from the perspective of alphas, it's no use to have a thicker detector. And in addition, other interactions, I mean photon interaction in silicon detector may only happen, and it disturbs the alpha spectrum. So, because the range of alphas is very short in samples, so what about this question? Let's suppose that you will obtain an environmental sample, such as soil sample, with mass of 100 grams or so. So you have to analyze polonium-210 from the sample. How to proceed then? I'm sure you can explain this. So what you have to do is you have to do probably radio element separation, and you must process the sample as a very, very thin layer so that you can have a good alpha spectrum. If the thickness is big, then there is a mess in the spectrum. However, you can analyze also those kind of spectra. I will show that later. All right, let's go through gamma ray interactions. Okay, these are the main mechanisms: photoelectric absorption, Compton scattering, and pair production. There is also Rayleigh scattering, but it's not very significant. So how these are visible in the gamma spectra? Let's see. So this happens in very low gamma energies, less than 100 kilo electron volts. So incoming low energy gamma ray is absorbed and an electron is ejected. However, what happens here is that electron shells, they are rearranged. For example, this photon kicks out this electron here, which means that there is an empty hole in the electron shell, and electrons coming from the outer shell may drop down, and that means there is an emission of X-rays. But if you want to calculate the kinetic energy of this electron, you have to take into account the binding energy. And as shown in one of the previous slides, you can see here the binding energy edges from different cells, M shell, L shell, and K shell. K shell is the innermost. This is L shell, etc., etc. So interaction probability depends very strongly on the atomic number, very strongly. And also inversely proportional to the energy of gammas. So this means that it is important only for low energy. And this means that this Z5, it means that lead absorbs more than, for example, copper. Let's look at Compton scattering. I'm so sure that you have looked through all these equations in your studies. Professor Compton investigated these things 100 years ago or something like that. If I remember it correctly, he got Nobel Prize for these equations. I'm not sure about that. So what happens here? So there's an interaction between the gamma ray and almost free orbital electron of the medium atom. So part of the gamma ray energy is transferred to the recoil electron. This is the recoil electron, this one. So this is in gamma ray spectrometry for environmental samples. I think this is one of the most important mechanisms. But also per production may happen in case of high energy gammas. But the energy must be 2 times the rest energy of electron. So it's in fact, it's a materialization of an electron and positron pair here close to the atomic nucleus. And the photon disappears. And the emission or the photon energy is divided between these two particles. And what may happen is annihilation of positron when it hits to normal material. So this is antimatter, this one. It may cause single or double so-called escape peaks and an annihilation peak, which is 511 kiloelectronvolts. All right, let's go on. So, if you take into account previous slides, it is so that size of the detector and also other things too determines how above mentioned interactions processes are visible in the gamma ray spectrum. So interactions may happen close to the surface of the detector or deep, or perhaps no interaction at all. It might happen. So let's assume that we have a very big detector, like this one. And let's assume that now in this picture I'm not considering the surface effects. That's why there is this hole. And photons are coming here this way. So detector is very big. What happens? So no particles are coming out of this detector, because the detector is very big. What happens? What we detect is we detect a full energy peak, nothing else. And this is a good thing, very good thing. However, if the detector is small, what happens? There are gamma ray interactions close to the surface of the detector. Okay? In the case of photoelectric absorption, photon disappears and the energy energies of the electrons are quite small, so that quite often it happens that all the energy stays in the detector, but not always. In case of Compton scattering, it may happen that photons escape the detector, and what we are seeing is the Compton background. And same thing holds for pair production. It may happen that the high energy electron, quite high energy, and positron, they may go out. So what we see here is, okay, we see of course full energy peak, which is our primary interest. We are interested mainly on these so-called photo peaks. We are not very much interested on these Compton areas. They are disturbing our spectrum analysis. As you will see perhaps today or tomorrow or Thursday. Let's look at the realistic detector. So its size is like your detectors here in your lab. So what does this intermediate mean? Its detector dimensions are comparable to the mean free path of secondary gammas. So it means that in several cases, all interactions or all electrons or photons, they stay inside the detector, but some may escape from the detector. This is the interior part of one of our decommissioned gamma detectors. So you can see here, this is the active part of the detector. So it's in fact, it's not very big. It's quite small, in fact. So this is the most important part of the detector. Of course, other parts are too. Important, but the detectors are not necessarily very big. So we can see here in the spectrum, we can see full energy peaks, but also so-called single escape peaks and double escape peaks. So do you have any questions in this phase? Is it too simple or too complex things? All right, let's continue. Please ask me if you have any uncertainties about these things I'm explaining. So, this is the simplified scheme of the detector response function. And what we are interested here is this full energy peak. We are not very much interested on these peaks or this background here. They are disturbing our gamma ray analysis. There are single escape peaks, double escape peaks. There may be annihilation peak, backscattering peak, X-ray peaks, etc. All right, let's explain some of these phenomena. Okay, let's assume that this is the detector and this is the lead shield here. So why we are using lead shield? To prevent photons coming from the walls or from your body to the detector. That disturbs the detection of photons coming from the sample itself. However, it's not necessarily a good thing that we have lead shield here, because there might happen secondary reactions. For example, in this case, let's assume that the source is here. Because of the Compton scattering, the photon may go through the detector and scatters here, so-called backscattering. So it would be better to measure photons without any lead shielding. But there is radiation all over in the university, so we have to use shielding. And in this case, it may happen that the photon goes this way to the lead sheet, then characteristic X-rays may come out there, and they are typically lead X-rays, energy of 80 kilo electron volts or so, 70. And also annihilation may happen, which means that this 511 peak may be detected, as shown here. So this is backscatter peak, this is X-ray peak, this is annihilation peak. You have to remember that these X-ray peaks can come also from the sample itself. You can please look at the LARA application that I showed you yesterday. In each emission, or practically in each emission or decay process, the nuclide emits also X-rays. However, their energies are much lower than typical gamma, so they are located also in this energy area here. All right. Okay, these are, I will show you some, let's see, all right. I will show you some examples. These examples, example spectra I obtained some years ago when I made efficiency calibration of our detectors. I used, in the efficiency calibration, I used two kind of sources. One source contained only lead 210, another source contained a mixture of different nuclides. I will explain this later, but this is this spectrum is from a americium-241 source. This is the main peak of americium. Let's zoom this spectrum. It's this one, so 59 kilo electron volts. There are other small peaks here. So what are these peaks? X-rays from americium, indeed. From what shell? They are in fact L X-rays, because K X-rays would be somewhere much higher, but americium do not emit very much K shell X-rays. All right. So, what's this, for example? Please, Avanis, you can explain. In fact, what happens in the detector when a photon goes there? It may happen so that K electron binding sorry, K electron emission energy is around 10 kilo electron volts. What may happen? Let's go back a little bit. Okay, let it be this one. If this interaction happens very close to the surface of the detector, what might happen? It might happen so that this K electron goes out of the detector. So there is an energy loss, and in fact, because the americium energy is so low, interactions mainly happen close to the detector surface. So it's a germanium escape peak. This one. So not all the energy is detected. And same thing also happens here in this area. Part of the electron energy stays in the detector, and other part of the energy is lost. So this is typical phenomenon in low energy gammas. All right. Let's look at cesium. As you know, the emission energy is 260. So what you can see here is a Compton edge, this one. There is a backscatter peak coming from the lead shield. Backscattering from there. And these are barium X-rays. And these are generated by the decay of cesium. The energies here, they are 32 and 37 kilo electron volts, if I remember this correctly. But you have to understand that cesium is a beta emission nuclide, so betas may also go to the detector. But we cannot see those. The beta energies are quite low in this nuclide. So the gamma detectors detect also betas. For example, I have done some measurements from strontium-90 by using our gamma ray spectrometer. So there are no peaks in that case. Okay, this is cobalt-60, very typical radionuclide in gamma ray laboratories. It mainly emits these two gammas here. Energies are shown here. Compton edge of this peak is located here, and from this peak it's located here. There is backscatter peak here. Annihilation peak is very small in this case, because the energies here, they are not very big. Annihilation peak would be quite big if the energies are higher. What is this peak? So you can see that there are some, in this case, if this level 3 goes directly to the base level, but the emission yield is very, very small. However, this is not very big, but anyway, it's quite big. Why? You have to understand that the energy resolution of typical multi-channel analysis, it's an order of microseconds. But this happens within nanoseconds or picoseconds or something like that. So it may happen that both of these photons goes to the detector basically at the same time from the point of view of the multi-channel analyzer. So it's a coincidence effect. And this coincidence effect is a very nasty effect, in fact. So in some nuclides have strong coincidences, and in the spectrum analysis phase, it may cause a lot of troubles. All right. Okay, this was it. Do you have any questions, comments? Is it too simple, this one?
From the forward spectra, I've seen the baseline is downward drafting. Why this happening?
Sorry?
The baseline is not in a straight line, it is downward drafting. Why that is happening in that spectrum?
You mean this?
That part is okay, but after the 1173 keV, the baseline is coming downwards.
You mean that?
After that, the baseline is coming downward.
Yes, it goes down.
Why it is happening?
Yeah.
Why it is not straight?
Multiple quantum scattering is possible. If you mean these counts here, yeah. And these counts here, they may be those cases when, for example, this photon stays, or the energy of this photon stays in the detector, but this photon coming at the same time, practically, the detector detects only part of this photon energy. So these are also coincidence, how to say this? These are because of the coincidences, but there is no peak in this case, because some of the peaks some of the photon energy came out of the detector. So coincidence effect means also that these peaks go lower. They are not anymore as high as normal. Any other comments, questions? All right, I hope that this presentation was not too simple for you, but I have to explain this. All right, but could we have a short break? What's the time now? Shall I have 13 minutes? So should we come back here 11 o'clock? No? Okay, thanks very much. Sorry, because of this noise, I can't hear. Can you?
Be louder. So can you explain coincidence effects?
Coincidence effect. Okay, once more. This is a detector, this one. This is a sample. Sample is usually put in this way, above the detector. What happens when there is radioactive material there? It might happen so that let's put it this way. So this is the detector. Let's assume that this is the sample. And a decay process happens, for example, here. So most of the photons go this way, this way, this way, but some of them goes here. And interactions happens here. But what's the coincidence effect? It's this one, because this cobalt-60, it emitted 2 photons at the same, more or less at the same time. It may happen that both photons are coming here. So what happens in the MCA, in the multi-channel analyzer? It doesn't detect energy of this photon only or this photon only. It detects some of these energies. So this is called as true coincidence. There is so-called random coincidences too, which is the fact that if this source is very active, several kilobecquerels or even megabecquerels, it may happen that let's assume that there is another nuclide here which also decays. Photons can go that way or this way. However, because the time resolution is only 1 microsecond order of magnitude in the MCA, it may happen that this photon is detected at the same time as this photon. So this is so-called random coincidence. It's a very nasty phenomenon, and it causes sometimes very big problems in the spectrum analysis, especially if there are several peaks in the spectrum. Did you understand this? Is it okay? Yeah, okay.
Some more questions?
Okay, you can ask me later. It's not a problem.
Yeah.
I answer.
You ask questions. Any doubt, you ask questions.
Yeah,
So she asked, he nicely explained it.
it's a good question.
Yeah.
Really. Because this is very important effect in gamma ray spectrometry, and as I told you, it disturbs quite often the analysis. All right, thank you very much.
Yeah.